The Theoretical Minimum by Leonard Susskind, Lecture 1, The Nature of Classical Physics. Somewhere in Steinbeck country, two tired men sit down at the side of the road. Lenny combs his beard with his fingers and says, "Tell me about the laws of physics, George." George looks down for a moment, then peers at Lenny over the tops of his glasses. "Okay, Lenny, but just the minimum." What is classical physics? The term classical physics refers to physics before the advent of quantum mechanics. Classical physics includes Newton's equations for the motion of particles, the Maxwell-Faraday theory of electromagnetic fields, and Einstein's general theory of relativity. But it is more than just specific theories of specific phenomena. It is a set of principles and rules, an underlying logic that governs all phenomena for which quantum uncertainty is not important. Those general rules are called classical mechanics. The job of classical mechanics is to predict the future. The great 18th century physicist Pierre-Simon Laplace laid it out in a famous quote. "We may regard the present state of the universe as the effect of its past and the cause of its future. An intellect which at a certain moment would know all forces that set nature in motion and all the positions of all the items of which nature is composed. If this intellect were also vast enough to submit this data to analysis, it would embrace in a single formula the movements of the greatest bodies of the universe and those of the tiniest atom. For such an intellect, nothing would be uncertain, and the future, just like the past, would be present before its eyes." In classical physics, if you know everything about a system at some instant of time, and you also know the equations that govern how the system changes, then you can predict the future. That's what we mean when we say that the classical laws of physics are deterministic. If we can say the same thing, but with the past and future reversed, then the same equations tell you everything about the past. Such a system is called reversible. Simple dynamical systems and the space of states. A collection of objects, particles, fields, waves, or whatever is called a system. A system that is either the entire universe or it's so isolated from everything else that it behaves as if nothing else exists is a closed system. Exercise 1. Since the notion is so important to theoretical physics, think about what a closed system is and speculate on whether closed systems can actually exist. What assumptions are implicit in establishing a closed system? What is an open system? To get an idea of what deterministic and reversible mean, we are going to begin with some extremely simple closed systems. They are much simpler than the things we usually study in physics, but they satisfy rules that are rudimentary versions of the laws of classical mechanics. We begin with an example that is so simple it is trivial. Imagine an abstract object that has only one state. We could think of it as a coin glued to the table, forever showing heads. In physics jargon, the collection of all states occupied by a system is its space of states, or more simply, its state space. The state space is not ordinary space. It's a mathematical set whose elements label the possible states of the system. Here the state space consists of a single point, namely heads, or just H, because the system has only one state. Predicting the future of this system is extremely simple. Nothing ever happens and the outcome of any observation is always H. The next simple system has a state space consisting of 2 points. In this case, we have one abstract object and two possible states. Imagine a coin that can either be heads or tails, H or T. See figure 1. In classical mechanics, we assume that systems evolve smoothly, without any jumps or interruptions. Such behavior is said to be continuous. Obviously, you cannot move between heads and tails smoothly. Moving, in this case, necessarily occurs in discrete jumps. So let's assume that time comes in discrete steps labeled by integers. A world whose evolution is discrete could be called stroboscopic. A system that changes with time is called a dynamical system. A dynamical system consists of more than a space of states. It also entails a law of motion or dynamical law. The dynamical law is a rule that tells us the next state given the current state. One very simple dynamical law is that whatever the state at some instant, the next state is the same. In the case of our example, it has two possible histories. H, 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 and T, 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 T. Another dynamical law dictates that whatever the current state, the next state is the opposite. We can make diagrams to illustrate these two laws. Figure 2 illustrates the first law, where the arrow from H goes to H, and the arrow from T goes to T. Once again, it is easy to predict the future. If you start with H, the system stays H. If you start with T, the system stays with T. A diagram for the second possible law is shown in figure 3, where the arrow leads from H to T and from T to H. You can still predict the future. For example, if we start with H, the history will be HT, 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 dot dot dot. If we start with T, the history is T, H, T, H, T, S, dot dot dot. We can even write these dynamical laws in equation form. The variables describing a system are called its degrees of freedom. Our coin has 1 degree of freedom, which we can denote by the Greek letter sigma. Sigma has only 2 possible values, sigma equals 1 and sigma equals -1, respectively, for H and T. We also use a symbol to keep track of the time. When we are considering a continuous evolution in time, we can symbolize it with T. Here we have a discrete evolution and we'll use N. The state of time n is described by the symbol sigma n, which stands for sigma at n. Let's write equations of evolution for the two laws. The first law says that no change takes place. In equation form, sigma n plus 1 equals sigma n. In other words, whatever the value of sigma at the nth step, it will have the same value at the next step. The second equation of evolution has the form sigma n plus 1 equals minus sigma n, implying that the state flips during each step. Because in each case the future behavior is completely determined by the initial state, such laws are deterministic. All the basic laws of classical mechanics are deterministic. To make things more interesting, let's generalize the system by increasing the number of states. Instead of a coin, we could use a 6-sided die, where we have 6 possible states. See figure 4. Now there are great many possible laws, and they are not so easy to describe in words or even in equations. The simplest way is to stick to diagrams such as figure 5. Figure 5 says that given the numerical state of a die at time n, we increase the state of 1 unit at the next instant n plus 1. That works fine until we get to 6, at which point the diagram tells you to go back to 1 and repeat the pattern. Such a pattern that is repeated endlessly is called a cycle. For example, if we start with 3, then the history is 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, and dot 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 continues. We'll call this pattern dynamical law number 1. Figure 6 shows another law, dynamical law number 2. It looks a little messier than the last case, but it's logically identical. In each case, the system endlessly cycles through the 6 possibilities. If we relabel the states, dynamical law 2 becomes identical to dynamical law 1. Not all laws are logically the same. Consider, for example, the law shown in figure 7. Dynamical law 3 has 2 cycles. If you start on one of them, you can't get to the other. Nevertheless, this law is completely deterministic. Wherever you start, the future is determined. For example, if you start at 2, the history will be 2, 6, 1, 2, 6, 1, and so on. And you will never get to 5. If you start at 5, the history is 5, 3, 4, 5, 3, 4, and so on. And you will never get to 6. Figure 6, dynamical law 2. Figure 7, dynamical law 3. Figure 8 shows dynamical law 4 with 3 cycles. Figure 8, dynamical law 4. It would take a long time to write out all the possible dynamical laws for a 6-state system. Exercise 2. Can you think of a general way to classify the laws that are possible for a 6-state system? Rules that are not allowed. The minus first law. According to the rules of classical physics, not all laws are legal. It's not enough for a dynamical law to be deterministic. It must also be reversible. The meaning of reversible in the context of physics can be described a few different ways. The most concise description is to say that if you reverse all the arrows, the resulting law is still deterministic. Another way is to say the laws are deterministic into the past as well as the future. Recall Laplace's remark on the quotes, "For such an intellect nothing would be uncertain, and the future, just like the past, would be present before its eyes." Closed quotes. Can one conceive of laws that are deterministic into the future but not into the past? In other words, can we formulate irreversible laws? Indeed we can. Consider figure 9. Figure 9, a system that is irreversible. The law of figure 9 does tell you, wherever you are, where to go next. If you are at 1, go to 2. If at 2, go to 3. If at 3, go to 2. There is no ambiguity about the future, but the past is a different matter. Suppose you are at 2. Where were you just before that? You could have come from 3 or from 1. The diagram just does not tell you. Even worse, in terms of reversibility, there is no state that leads to 1. State 1 has no past. The law of figure 9 is irreversible. It illustrates just the kind of situation that is prohibited by the principles of classical physics. Notice that if you reverse the arrows in figure 9 to give figure 10, the corresponding law fails to tell you where to go in the future. Figure 10, a system that is not deterministic into the future. There is a very simple rule to tell when a diagram represents a deterministic reversible law. If every state has a single unique arrow leading into it and a single arrow leading out of it, then it is a legal deterministic reversible law. Here is a slogan. There must be one arrow to tell you where you are going and one to tell you where you came from. The rule that dynamical laws must be deterministic and reversible is so central to classical physics that we sometimes forget to mention it when teaching the subject. In fact, it doesn't even have a name. We could call it the first law, but unfortunately there are already two first laws, Newton's and the first law of thermodynamics. There is even a zeroth law of thermodynamics. So we have to go back to a minus first law to gain priority for what is undoubtedly the most fundamental of all physical laws, the conservation of information. The conservation of information is simply the rule that every state has one arrow in and one arrow out. It ensures that you never lose track of where you started. The conservation of information is not a conventional conservation law. We will return to conservation laws after a digression into systems with infinitely many states. Dynamical systems with an infinite number of states. So far, all our examples have had state spaces with only a finite number of states. There is no reason why you can't have a dynamical system with an infinite number of states. For example, imagine a line with an infinite number of discrete points along it, like a train track with an infinite sequence of stations in both directions. Suppose that a marker of some sort can jump from one point to another according to some rule. To describe such a system, we can label the points along the line by integers the same way we label the discrete instance of time above. Because we have already used the notation n for discrete time steps, let's use the uppercase N for the points on the track. Our history of the marker would consist of a function uppercase n, telling you the place along the track n at every time n. A short portion of this state space is shown in figure 11. Figure 11, state space for an infinite system. A very simple dynamical law for such a system, shown in figure 12, is to shift the marker one unit in the positive direction at each time step. Figure 12, a dynamical rule for an infinite system. This is allowable because each state has one arrow in and one arrow out. We can easily express this rule in the form of an equation. n plus 1 equals n plus 1. Here are some other possible rules, but not all are allowable. n plus 1 equals n minus 1, n plus 1 equals n plus 2, n plus 1 equals n square, and others. Exercise 3. Determine which of the dynamical laws shown in equations 2 through 5 are allowable. In equation 1, wherever you start, you will eventually get to every other point by either going to the future or going to the past. We said that there is a single infinite cycle. With equation 3, on the other hand, if you start at an odd value of n, you will never get to an even value, and vice versa. Thus, we say there are two infinite cycles. We can also add quantitatively different states to the system to create more cycles, as shown in figure 13. Figure 13, an infinite configuration space into finite and infinite cycles. If we start with a number, then we just keep proceeding through the upper line, as in figure 12. On the other hand, if we start at A or B, then we cycle between them. Thus, we can have mixtures where we cycle around in some states, while in others we move off to infinity. Cycles and conservation laws. When the state space is separated into several cycles, the system remains in whatever cycle it started in. Each cycle has its own dynamical rule, but they are all part of the same state space because they describe the same dynamical system. Let's consider a system with 3 cycles. Each of states 1 and 2 belongs to its own cycle, while 3 and 4 belong to the third. See figure 14. Figure 14, separating the state space into cycles. Whenever a dynamical law divides the state space into such separate cycles, there is a memory of which cycle they started in. Such a memory is called a conservation law. It tells us that something is kept intact for all time. To make the conservation law quantitative, we give each cycle a numerical value called Q. In the example in figure 15, the 3 cycles are labeled Q equals plus 1, Q equals minus 1, and Q equals 0. Whatever the value of Q, it remains the same for all time because the dynamical law does not allow jumping from one cycle to another. Simply stated, Q is conserved. Figure 15, labeling the cycles with specific values of a conserved quantity. In later chapters, we will take up the problem of continuous motion in which both the time and the state space are continuous. All of the things that we discussed for simple discrete systems have their analogs for the more realistic systems, but it will take several chapters before we see how they all play out. The limits of precision. Laplace may have been overly optimistic about how predictable the world is, even in classical physics. He certainly would have agreed that predicting the future would require a perfect knowledge of the dynamical laws governing the world, as well as the tremendous computing power that he called an, under quotes, intellect vast enough to submit this data to analysis, closed quotes. But there is another element that he may have underestimated: the ability to know the initial conditions with almost perfect precision. Imagine a die with 1,000,000 faces, each of which is leveled with a symbol similar in appearance to the usual single-digit integers, but with enough slight differences so that there are 1,000,000 distinguishable levels. If one knew the dynamical law, and if one were able to recognize the initial level, one could predict the future history of the die. However, if Laplace's vast intellect suffered from a slight vision impairment so that he was unable to distinguish among similar levels, his predicting ability would be limited. In the real world, it's even worse. The space of states is not only huge in its number of points, it is continuously infinite. In other words, it is leveled by a collection of real numbers, such as the coordinates of the particles. Real numbers are so dense that every one of them is arbitrarily close in value to an infinite number of neighbors. The ability to distinguish the neighboring values of these numbers is the resolving power, under quotes, of any experiment, and for any real observer, it is limited. In principle, we cannot know the initial conditions with infinite precision. In most cases, the tiniest differences in the initial conditions, the starting state, leads to large eventual differences in outcomes. This phenomenon is called chaos. If a system is chaotic, most are, then it implies that however good the resolving power may be, the time over which the system is predictable is limited. Perfect predictability is not achievable simply because we are limited in our resolving power. Interlude 1. Spaces, Trigonometry, and Vectors. Where are we, George? George pulled out his map and spread it out in front of Lenny. We're right here, Lenny. Coordinates 36.60709 north, minus 121.618652 west. Huh? What's a coordinate, George? Coordinates. To describe points quantitatively, we need to have a coordinate system. Constructing a coordinate system begins with choosing a point of space to be the origin. Sometimes the origin is chosen to make the equations especially simple. For example, the theory of the solar system would look more complicated if we put the origins anywhere but at the sun. Strictly speaking, the location of the origin is arbitrary. Put it anywhere. But once it is chosen, stick with the choice. The next step is to choose three perpendicular axes. Again, their location is somewhat arbitrary as long as they are perpendicular. The axes are usually called x, y, and z, but we can also call them x1, x2, and x3. Such a system of axes is called a Cartesian coordinate system, as in Figure 1. Figure 1, a three-dimensional Cartesian coordinate system. We want to describe a certain point in space. Call it P. It can be located by giving the x, y, z coordinates of the point. In other words, we identify the point P with the order triple of numbers x, y, and z. See Figure 2. A point in Cartesian space. Figure 2. The x-coordinate represents the perpendicular distance of P from the plane defined by the setting x equals 0. The same is true for y and z coordinates. Because the coordinates represent distances, they are measured in units of length, such as meters. Figure 3. A plane defined by setting x equals 0 and the distance to P along the x-axis. When we study motion, we also need to keep track of time. Again, we start with an origin, that is, the 0 of time. We could pick the Big Bang to be the origin, or the birth of Jesus, or just the start of an experiment. But once we pick it, we don't change it. Next, we need to fix a direction of time. The usual convention is that positive times are to the future of the origin and negative times are to the past. We could do it the other way, but we won't. Finally, we need units for time. Seconds are the physicists' customary units, but hours, nanoseconds, or years are also possible. Once having picked the units and the origin, we can label any time by a number t. There are two implicit assumptions about time in classical mechanics. The first is that time runs uniformly. An interval of 1 second has exactly the same meaning at one time as at another. For example, it took the same number of seconds for a weight to fall from the Tower of Pisa in Galileo's time as it takes in our time. 1 second meant the same thing then as it does now. The other assumption is that times can be compared at different locations. This means that clocks located in different places can be synchronized. Given these assumptions, the four coordinates x, y, z, and t define a reference frame. Any event in the reference frame must be assigned a value for each of the coordinates. Given the function ft equals t squared, we can plot the points on a coordinate system. We will use one axis for time t and another for the function ft. See Figure 4. Figure 4. Plotting the points of ft equals t squared. We can also connect the dots with curves to fill in the spaces between the points. Figure 5. Joining the plotted points with curves. In this way, we can visualize functions. Exercise 1. Using a graphing calculator or a program like Mathematica, plot each of the following functions. See the next section if you are unfamiliar with the trigonometric functions. ft equals t power 4 plus 3t power cube blah blah blah, gx sin x minus cos x, and that function. Plot them out, alright? Trigonometry. If you have not studied trigonometry, or if you studied it a long time ago, then this section is for you. We use trigonometry in physics all the time. It is everywhere. So you need to be familiar with some of the ideas, symbols, and methods used in trigonometry. To begin with, in physics, we do not generally use the degree as a measure of the angle. Instead, we use the radian. We say that there are 2 pi radians in 360 degrees, or 1 radian equals to pi by 180 degree. Thus, 90 degree is pi by 2 radians, and 30 degree is pi by 6 radians. Thus, a radian is about 57 degree. See Figure 6. The trigonometric functions are defined in terms of properties of right angles. Figure 7 illustrates the right angle and its hypotenuse c, base b, and altitude a. The Greek letter theta is defined to be the angle opposite the altitude. and the Greek letter phi is defined to be the angle opposite the base. Figure 6. The radian as the angle subtended by an arc equal to the radius of the circle. Figure 7. A right angle triangle with segments and angles indicated. We define the function sine, cosine, and tangent as the ratios of the various sides according to the following relationships. Sine theta equals a by c, cos theta equals b by c, tan theta equals a by b, or sine theta by cos theta. We can graph these functions to see how they vary. Figure 8. Graph of sine function. Figure 9. Graph of the cosine function. Figure 10. Graph of the tangent function. There are a couple of useful things to know about the trigonometric functions. The first is that we can draw a triangle within a circle with the center of the circle located at the origin of a Cartesian coordinate system, as in Figure 11. Figure 11. The right triangle drawn in a circle. Here the line connecting the center of the circle to any point along its circumference forms the hypotenuse of a right triangle, and the horizontal and vertical components of the point are the base and altitude of that triangle. The position of a point can be specified by two coordinates, x and y, where x equals c cos theta and y equals c sin theta. This is a very useful relationship between right triangles and circles. Suppose a certain theta is the sum or difference of two angles using the Greek alphabets alpha and beta. We can write this angle theta as alpha plus minus beta. The trigonometric functions of alpha plus minus beta can be expressed in terms of the trigonometric functions of alpha and beta. For example, sine alpha plus beta equals sine alpha cos beta plus cos alpha sin beta, and then similar other relationships. And finally, a very useful identity is sine square theta plus cos square theta is 1. Notice the notation used here. Sine square theta equals sin theta times sin theta. This equation is the Pythagorean theorem in disguise. If we choose the radius of the circle in Figure 11 to be 1, then the sides a and b are the sine and cosine of theta, and the hypotenuse is 1. Equation 1 is the familiar relation among the three sides of the right angle triangle a square plus b square equals c square. Vectors. Vector notation is another mathematical subject that we assume you have seen before, but just to level the playing field, let's review vector methods in ordinary three-dimensional space. A vector can be thought of as an object that has both a length or magnitude and a direction in space. An example is displacement. If an object is moved from some particular starting location, it is not enough to know how far it has moved in order to know where it ends up. One has to know the direction of the displacement. Displacement is the simple example of a vector quantity. Graphically, a vector is depicted as an arrow with a length and direction, as shown in Figure 12. Figure 12. A vector r in Cartesian coordinates. Symbolically, vectors are represented by placing arrows over them. Thus, the symbol for displacement is r. The magnitude or length of a vector is expressed in absolute value notation. Thus, the length of vector r is denoted by the modulus r. Here are some operations that can be done with vectors. First of all, you can multiply them by ordinary real numbers. When dealing with vectors, you will often see such real numbers given the special name scalar. Multiplying by a positive number just multiplies the length of the vector by that number. But you can also multiply a negative number, which reverses the direction of the vector. For example, minus 2 vector r is the vector that is twice as long as vector r, but points in the opposite direction. Vectors may be added. To add vector a and vector v, place them as shown in Figure 13 to form a quadrilateral. This way the directions of the vectors are preserved. The sum of the vectors is the length and angle of the diagonal. Figure 13. Adding vectors. If vectors can be added, and if they can be multiplied by negative numbers, then they can be subtracted. Exercise 2. Work out the rule for vector subtraction. Vectors can also be described in component form. We begin with the three perpendicular axes x, y, and z. Next, we define three unit vectors that lie along these axes and have unit length. The unit vectors along the coordinate axis are called basis vectors. The three basis vectors for Cartesian coordinates are traditionally called I, j, and k. See figure 14. More generally, we write E1, E2, and E3 when we refer to x1, x2, x3, where the symbol known as the caret tells us we are dealing with unit or basis vectors. The basis vectors are useful because any vector v can be written in terms of them in the following way. Vector v equals vxi plus vyj plus vzk. Figure 14. Basis vectors for a Cartesian coordinate system. The quantities vx, vy, and vz are numerical coefficients that are needed to add up the basis vectors to give vector v. They are also called the components of vector v. We can say that equation 2 is a linear combination of basis vectors. This is a fancy way of saying that we add the basis vectors along with any relevant factors. Vector components can be positive or negative. We can also write a vector as a list of its components. In this case, vx, vy, vz. The magnitude of a vector can be given in terms of its components by applying the three-dimensional Pythagorean theorem. The magnitude of vector v equals square root of vx square plus vy square plus vz square. We can multiply a vector v via a scalar alpha in terms of components by multiplying each component by alpha. Alpha vector v equals alpha vx, alpha vy, alpha vz. We can write the sum of two vectors as the sum of the corresponding components as such. For example, the sum of two vectors a plus b, its x component equals the sum of the x components of individual vectors a x plus bx, and similarly for other x's. Can we multiply vectors? Yes, and there is more than one way. One type of product, the cross product, gives another vector. For now, we will not worry about the cross product and only consider the other product, the dot product. The dot product of two vectors is an ordinary number, a scalar. For vectors a and b, it is defined as follows. Vector a dot vector b equals modulus of a times modulus of b times cos theta. Here, theta is the angle between the vectors. In ordinary language, the dot product is the product of the magnitudes of the two vectors and the cosine of the angle between them. The dot product can also be defined in terms of components in the form vector a dot vector v equals ax bx plus ay by plus az bz. This makes it easy to compute dot products given the components of the vectors. Exercise 3. Show that the magnitude of a vector satisfies this condition. Modulus of vector a square equals vector a dot vector a. Exercise 4. Let ax 2, ay minus 3 and az 1 and bx minus 4, by minus 3 and bz 2. Compute the magnitude of vector a and vector v, their dot product, and the angle between them. An important property of the dot product is that it is zero if the vectors are orthogonal, that is, perpendicular. Keep this in mind because we will have occasion to use it to show the vectors are orthogonal. Exercise number 5. Determine which pair of vectors are orthogonal. 1, 1, 1, 2, minus 1, 3, 3, 1, 0, minus 3, 0, 2. Exercise 6. Can you explain why the dot product of two vectors that are orthogonal is 0?